of FDM 3D printed transtibial prosthetic sockets. So I do not have any conflicts of interest to declare. Starting a bit with our presentation outline, I'll start with providing some background and some of the motivation behind our study, moving on to our framework and how we approached some of our research questions, moving on to our project results, and finishing off with some of the final discussion items and conclusions we drew from our study. So the work I'll be presenting today is the work of my master's thesis, and it was a collaborative project developed through UNB's Marine Additive Manufacturing Center of Excellence, and also Beacon Ortho, Prosthetics and Orthotics, located in St. John, New Brunswick. Our main objective here, and as you've heard throughout this conference and throughout the day, lots of 3D printing talk and lots of talk about the durability of some of these manufacturing methods. So our overall aim here was we were looking to evaluate the structural strength of 3D printed sockets. Specifically, we were looking at transtibial trial sockets made with FDM 3D printing. Just to provide a bit of background, so when additive manufacturing was first developed, it was developed as a rapid prototyping technique, so a method to produce a prototype before making a finalized part. One of the key advantages that quickly emerged with additive manufacturing was that it could produce complex geometries that were difficult and most times impossible to achieve with more conventional manufacturing methods. And we've talked about many of the advantages of additive manufacturing, in the conference, but for trial sockets, which essentially serve as a rapid prototype with inherently complex geometry, it makes them particularly well suited to utilizing this technology. So although various additive manufacturings exist, the premise of it is that they all rely on this layer by layer fabrication method. They differ in the sense of what is the method or the energy that creates and joins these layers. For trial socket production, FDM, so fused deposition modeling, enables those benefits of additive manufacturing, but it remains a practical and accessible method to clinics, especially for smaller scale clinics. And just to touch briefly, if you're not familiar with FDM, it feeds a thermoplastic filament through a heated nozzle and extrudes the material strategically onto a build plate to build a formed part. For our study, we focused on a specific use case with a fixed set of print parameters, focusing on a material called, I'm not going to read that name, it's called PCTG. That's the longest word I've ever seen. Some of the benefits of this material, it's been used within the industry previously, and some of its typical applications include things like food and water containers, healthcare, and packaging components, and et cetera. For reason we're exploring this material, it has high clarity, and it has good dimensional stability, and it's easily processable, which makes it easy to print in comparison to some of the higher complex materials. This also makes it easy to modify, which is important for trial sockets. And in terms of its mechanical properties, it's a very tough material and it's very impact resistant. So this brings us to our motivation and the thing that's been highlighted many times throughout the last couple of days. 3D printed sockets don't have that long-standing historical use case that supports their structural strength like some of the more traditional socket fabrication methods. And for load-bearing lower limb devices like TT sockets, it's highly reported that the apprehension of the structural integrity of these parts is one of the key limiting factors to accepting and adopting these technologies. The reason for this apprehension relies on that layer by layer manufacturing method. And this is because this method creates what's called anisotropic material behavior, which means the materials and the parts produced with these manufacturing methods is directionally dependent behavior. And so if we look here closely at kind of what's going on, as these layers are deposited, there's a partial bond between the filaments, but there's also these little voids that lead to this directional dependent behavior. Here I want to illustrate here and further explain when I talk about that directional dependent behavior. If you look at the bottom image here, this horizontal material specimen, if the load is applied with the direction of those shown in those black arrows, it's applied parallel to the filament strands, which means the strength relies on the filament strand itself. However, if we look here at the vertical sample in the middle here, if the load's applied perpendicular to the layer lines, the strength then relies on the quality of the bond between the filaments rather than the filament itself. Therefore, there's a different material properties for the filament you're using based off of the quality of the bond, not just the bulk material properties of that filament. And then we get into all the different angles you can print at with 3D printing, which is an additional level of complexity. So this brings us to our project framework. So we were aiming to evaluate and address some of these concerns pertaining to structural integrity for our use case, and overall aiming to support safe and evidence-based adoption of these methods. Our study relied on 3 key components, the first of which was experimental material characterization. And so we tested material coupons in order to understand some of that directional dependent behavior I'm talking about. We then performed experimental socket testing, and that all led into our computational modeling work. I'll touch on these other components a little bit, but most of what I'll talk about today is our experimental socket testing. But just to touch a bit on our overall framework, we performed our experimental testing in parallel with the model development, and then used the data from our material test and our socket test to inform and validate that computational model. So touching a bit on our material characterization test, so we performed tensile and compressive test of 3 different orientations of material samples. A horizontal sample, which was printed flat to the build plate, a vertical sample printed perpendicular to the build plate, and an oblique sample printed at a 45-degree angle. And I won't go into much of what this plot is, but what I want to highlight here is that we see in the different colors here shown in black, red, and blue that there is different material behavior between those different print orientations. But we also see, when we compare the solid lines to the dotted lines, that there's a difference in material behavior between the tensile and the compressive behavior as well. So this brings us into our socket testing setup. So our socket testing was guided by ISO 22675, but we also referenced ISO 10328 for the overall prosthesis sample, and particularly when we were talking about the mock residual limb. How this test works is that it applies a load with a large actuator at the top of the socket, and a tilting axis at the bottom of the sample rotates to apply the loading direction to achieve those representative loading conditions that represent gait. There's both static and cyclic loading protocols within this testing standard, which we performed with our testing. This is a little bit of our socket testing sample, and so the mock residual limb had an embedded mandrel that allowed our socket sample to actually be mounted within the machine. For our mock residual limb, this was a rigid polyurethane limb model made with a 3D printed mold. There's an aluminum mandrel embedded within the limb model, and we also had a void 5 centimeters of the distal end in order to meet some of the requirements of the standard. We also look here, if you look at image C on the slide, this is the distal end attachment design we were exploring. And just out of curiosity, how many of you have maybe seen or used this design with these embedded dowel nuts within the distal end? No, not many. Okay, yeah, it has been used. There's been a few reported cases. That was mostly for my own curiosity. So all of our socket tests were performed. We partnered with the University of Applied Sciences of Thomas More in Belgium, and we partnered with them partially because they have this machine here, which was specifically designed to test to ISO 22675. So all of the socket tests were performed there within their Mobilab and CARE research group, and we performed all of our socket testing to the P5 level. So for the static testing portion, the standard includes proof strength tests and ultimate strength tests for 2 loading conditions. And so the first condition represents heel loading, and the second condition represents forefoot loading. For our cyclic test, we use a prescribed loading profile as well as a prescribed profile for that tilting axis position in order to represent and simulate a step. For our testing, we performed 250,000 cycles, and that was to represent roughly 3 months of wear, roughly the amount for what would be for a trial socket. I don't know if I have a video here of our cyclic testing. I don't know if it'll play, but we're going to try. Yeah, it won't play, but if you're interested in seeing the video, absolutely come and see me. It's cool to see it walk. yeah, it's a cool thing to see the socket walk, but come see me, I'll show you that video for sure. For our socket testing, we performed our testing on 3 socket samples, 2 of which were FDM 3D printed, 1 of which was a blister molded thermalin socket. This allowed us to compare results across fabrication methods, but we also tested across different shapes of residual limbs. So we tested a longer, more cylindrical limb, which we identified as geometry number 1, and a more shorter conical limb identified as geometry number 2. And so you see here, and I'll reference them a little bit throughout our results, they were identified by their geometry and their fabrication methods. So we have sample 3DP1, 3DP2, and TP1. So this brings us to the results of our socket testing. First of all, for our static results, all of the sockets withstood the required level of loading without any visible fractures or damage within the sockets. For our dynamic or our cyclic testing, both sockets with geometry number 1, so the longer, more cylindrical limb shape, withstood the 250,000 cycles without any damage. However, our 3DP2 sample experienced fatigue-related failures within testing within those 250,000 cycles. So here, here's a look at kind of the 2 key points we saw the fractures. The first location we saw was within the distal end surrounding that dowel nut embedded that I talked about a little bit earlier. Kind of around the circumference, we saw those fractures surrounding there. Secondly, we saw some fractures, some smaller fractures within the lateral wing of the socket. So this might look a little crazy, but this was our further analysis. It's called scanning electron microscopy. And so this allowed us to look very closely at the fractures to try and understand kind of the behavior of the failure. If you look here in image A, we actually see that the fracture starts by what's called layer delamination. And so the bond between those filament layers is actually being broken and starting the fracture. However, if you look at image B, we also see fracture across the filament strand itself, indicating the failure from that bulk material. Here, this image looks very closely, and I want to highlight, if you kind of see these concentric bands here further on the right side of the image, highlighted in yellow here, these concentric bands tell us that it is the fatigue failure, it's the repeated loading that caused the failure within the socket. It's not, the static one big load, it's that repeated loading that's causing that fracture. So I'll touch a little bit on our computational model. And so what we did to validate our computational model was compare what our model was predicting as areas of high stress and therefore more likely for failure to the actual observed failures within the socket. So you see here the areas in red are areas our model is saying there's a high stress, and you can see the correlation here between that observed fracture. And we see that again in our second location. And so to use this model, we'd like to, without having the testing of the socket is quite time consuming. So to be able to simulate that without having to test sockets is some of the utility of this model. So this brings us to some of the discussion and conclusions. So it doesn't show my image there, but the fatigue behavior here is what we saw and report as the more important failure criterion here. Even though the statics withstood 5 kilonewtons of load statically, we saw that our second socket shape couldn't withstand the repeated loading it was subject to, which is important when you're thinking about the real life use case of a trowel socket. We also saw within our failure that it followed the printed structure. So it's the failure of the socket is related to that additive manufacturing process. Some of the things I want to highlight, especially for a clinical group, is some of the things that impact the loading conditions on the socket. Things like geometry, alignment, suspension, all these things change the loading conditions experienced by the socket. So when we think about strength, just because one specific socket configuration is strong enough, that doesn't mean it's universally applicable. It's important that we consider all these conditions and all these things that play a part in loading on socket. An example we saw of this within our study was the choice of prosthetic foot. And so because within that that standard, we use a foot to mount the sample within the machine. We saw within our 3D P2 sample, we saw some fractures, but we also use a stiffer foot. And so although there's further analysis to be made on these results, this just highlights that, you know, there's different things that impact the structural conditions that a socket's being subject to. Another thing I'd like to really highlight is that additive manufacturing introduces so many more design variables, right? And if you have experience with any type of 3D printing, you start to understand these design variables to consider. And one of the things I really want to focus on is the distal attachment design. And so here, when we use this distal attachment design, so these steel nuts here are in the socket. The problem with these is that there's a large amount of force on a small amount of area, which leads to a high amount of stress, and which is part of the reason we saw the fractures, you know, surrounding that dowel nut. And so it's important when you're considering all these things that we think about these things and think about how these sockets are being loaded. I can't go through this testing protocol without highlighting the limitations of the ISO testing protocols themselves. It's been heavily acknowledged throughout a few papers and lots of our colleagues that you know, these standards were not specifically designed for prosthetic socket testing. There's some work being done on getting better standards, more repeatable standards, and it's important that we work on this. But what happens with these standards, there's a lot of things that are kind of left to decide upon yourself when you're doing the testing. So highlighted in yellow here are all the components that we had to make our own choices about. And what happens here is that when trying to compare to other studies, because these choices were made based off of who was doing the test, there's variability not only within methodology, but within the results as well that make it difficult to draw any meaningful conclusions when trying to compare any of studies. So now it comes to key takeaways, and I've lost my words magically here. But my first point is that I don't know where the pose or like. My first main key takeaway is that the fatigue behavior is important, right? Just because a socket can withstand a great amount of static load. I know, and there was some great work by the group at Sunnybrook as well about the durability and fatigue behavior. But the fatigue behavior is important. Secondly, I want to highlight one of the key takeaways of the importance of considering all these clinical choices and these design variables with sockets and how they impact our structural conditions on a socket. I'd like to also highlight that as if any manufacturing method, any type of 3D printing, it's important that we understand the strength and its limitations. I heavily highlight, you know, the directionally dependent behavior of FDM printing. That's not to say that FDM is, you know, no good and it changes behavior and direction. No, it's just important that we understand this, and when we're designing these things, that this is something we think about and consider. And this brings me to my final point. We need to start testing more and testing all these different parameters in order to build this understanding. Lastly, I'd like to thank everyone who collaborated on this project. It was a big collaboration between many groups. First of all, the team at Beacon Ortho. This project has been in the works for about 2 years now, and I very much appreciate the opportunity to work with the wonderful team there. I'd also like to thank the MAMC team, so my research team at the University of New Brunswick, for all their help, my supervisors, Dr. Mohsen Mohammadi and Dr. Michelle Kwok, and as well as Tom and Daniel from the University of Thomas More in Belgium for all of their help with the socket testing. Now I'd like to take some questions, and si vous voulez demander des questions en français, je peux faire ça aussi. So. That's it. Yep.
Were you actually able to get a perfectly vertical transtibial socket printed with the layers going vertically?
So the way the material model works, it's kind of complex into the material behavior. So when we're building our computational model, it's not to say the socket's 100% vertical. It's not to say the socket's 100% horizontal. We're actually taking a bit of information of each of those elements in order to build a material model that says it's pushing this direction. Okay, what's going to happen? And it's incorporating all those elements, because the socket orientation varies, right? It's not perfectly throughout, like especially with an FDM, and so we take those elements of the different directions to inform the model. It's not necessarily saying, okay, it's fully vertical, it's fully horizontal. That was a large part of the model, the computational model framework was establishing that. So. Yep.
Great presentation.
Thank you.
Great work. Learned a lot.
Yeah. Yeah.
It's great. Just one small question has been in my mind too. I see that one of the pictures, the tibia is located sort of centrally. Is that a limitation in terms of just a setup, or is there a reason for that?
Within the dummy, you mean? Like,
yes.
Yeah. So with the mock residual limb setup, and that's a tough one because of it's kind of within the standard. It's not very clearly defined, right? And so what the aim was there is that the standard defines, the loading offsets to try and achieve those representative loading lines. And so the position of that mandrel was as close as we could get to the centers in order to do kind of what we needed to get it where it needed to be for the standard. Yeah. Yeah. Yep. Yep.
So since the was failing along layer lines, do you have any other materials that have better adhesion?
Well, that's a big question, right? This is time to understand how this is going, and then further developing, testing different materials and testing different things, and trying all these things, and your print parameters have an effect. There's all these things that come into play with the quality of the bond between the layers, and it's a lot of work to try and you can't cover that within this project, but there's definitely some more future work in terms of, okay, how do we get really good bonds? What materials do that? And it's also like what's needed clinically too, right? Like what's important clinically. So. Well, thank you very much. I very appreciate your time.